Hello everyone, it's September 30th. Actually not. Right now, I'm actually already October the 1st. It's past midnight. This is the latest. I've done this for a very long time. Today we had, a lot of things happened today, I think. I mean, mainly we are dealing with an email issue. So we launched an app, right? And then when users sign up for the app will send a verification email to user's email address to verify whether the user's email address is correct. And it just turns out that the email address sent from Firebase is blocked by Outlook, which is the email server used by the user. I think I talked about this maybe yesterday or the day before yesterday. So we try to find a solution to it, and then we try a lot of iterations. And then today, what we did was we migrated. So we're not using Firebase's email service anymore. We migrate to Mailgun, and the ideal is if the sender becomes Mailgun, and then Mailgun we also set it up to our own domain, to our company's domain, and we think that will have a positive effect on Outlook. They'll give us a pass, but they do not. Right, the email we send from Mailgun via Firebase, but eventually from Mailgun, it still doesn't land. Still doesn't land on the Outlook account. So we didn't know what to do, and we just play around with different try and error, and eventually we will figure out is that Outlook account needs to be warm up with our domain name, right? So if we send an email, the verification email, which has a link in it, if we send that directly, it's gonna get flagged and not even landing in the spam, in the junk mail. But if we send an email which does not contain any link, which is like pure either HTML or pure just text, and that email will land in the box, in the inbox, not even junk mail. So that is a warm-up. So if we have sent a warm-up email to Outlook, and Outlook accepts it, and then put it in the main inbox, after that, we can send email with a link in it, and we will land in the junk mail, right? So this is what we found. So in order to solve this problem, solve this verification email and never landing problem, we need to send a warm-up email first, right? Send a non-spam, pure text warm-up email first, and follow up with the actual email with a link in it. So this is all good, and we thought we had found a solution. Now we just need to craft a warm-up email, and it cannot just be like, oh, this is a warm-up email, right? We want it to be, say, a welcome email, welcome on board, thank you very much for downloading our app. So we created a HTML version of that email, and then everything works perfectly until we want to include the company logo. See, the company logo, we can do it two ways, right? We can either put the raw SVG code in the HTML, or we can use an image, a JPEG, a PNG, whatnot. So we tried the SVG route because it's better. We thought by it can scale and everything would look nice. And using my email, like a third-party email manager, and then I can see the SVG, everything is fine. But when we log into Gmail directly, Gmail doesn't display it. And when we log into Outlook directly, Outlook doesn't display it. So the logo is not there. So okay, so we don't use SVG. Let's try PNG, right? Let's try an image. And to send an image, we need to store the image somewhere, right? So we store an image in Firebase. We have storage, and then we pull it down from Firebase with a link, and then Gmail displays it, perfect, and Outlook spams it. I think because we have a link. We have a link, and then the link's domain name doesn't match the sender's domain name, because the sender's domain name is our company's domain, and the link's domain name is a Firebase. So Outlook spams it. And that's exactly the opposite of what we want. We want this welcome email, the warm-up, to be landing in the actual inbox, not in the spam. But by including a link to our logo image, it goes to the spam. So we're getting stuck between a rock and a hard place. Either we use SVG and the email will go into the actual inbox, but Outlook does not display the logo, or we use the logo image with a link to the logo image, and then Outlook will display it, but it lands in the junk. So like we don't like either option, but I'm leaning towards the no logo. I'd rather have no logo than the warm-up email landing in the junk mail. But anyway, this is just all frustrating experience, right? You think you have done everything on your part, but there are other things out there. I feel like this is like out of our control. And from what I'm reading, the email display the technology is far behind the browser. Like most browsers, almost all browsers support SVG right now, but not all email clients do that. Actually, not even half like can do it. So anyway, that's my rant. Let's go to what we have today. All right, we have given an integer array nums and integer k. Return true if it is possible to divide this array into k non-empty subsets whose sums are equal. So we can divide into 4 subsets. So it doesn't have to be following any order. So just divide into subset 5, 1, 4, 2, 3, and 2, 3, okay? And this is false because we cannot do 3. The length is 16. What? The frequency of each element is in the range of 1 to 4. What does that mean? Oh, the number of times they will appear. But the length is only 16. The length is 16. Alright, but we divide it into k parts. There's gotta be a lot of different ways to do the division. Okay, so what's on your mind? Well, my first instinct is to sort it. We needed some order. So let's sort it. Let's go for the first example and then see what's going to happen if we sort it. So if we sort it, we have 1, 2, 2, 3, 3, 4, 5, right? After we sort it, we have this. Now what? Now we want to see is if it's possible to divide it into 4 subsets. Well, we can compute the sum of everything. But if we can divide it into 4 subsets, then we have the actual value. Oh, that's why the example 2 failed, because the sum is 10. We cannot divide it into 3 equal sums. And this one, the sum is 1 plus 4 is 5, plus 8, plus 6 is 11, 15, 20, right? So that's 20. And then if we divide it by 4, that gives us 5, which means we need to form 5. So we go through it, see if we can find 5. And because we have sorted, so we know that it has to be the small plus the big, right? It couldn't be the other way around. Think about it. Like, okay, so we go from big to small, right? If the big value, the largest value, is larger than what we allowed, that's a no-go, right? We immediately can ignore it. So yeah, we have to go from the big. So the big one, 5. So immediately we take that out. It's good. Now the next one is 4. So 4 we need 1, right? And we have 1. So that's deterministic. So we take it. 3 we need 2, deterministic. 3 we need 2. Now, the first example is deterministic. Now what can happen is it's not deterministic. Like, let's say we have a value, right? Let's say 3. 3 we need 2, but we have both 2 and we have 1s. Now that is a question. Which one you pick? Do you pick 2 or do you pick 2 1s? I think that is the difficult part. But maybe you can just DFS it, right? Not DFS, backtracking it. Can we backtracking it? And we always focus on the big value, right? So we get a big value, and then big value, we need something, right? We need some value to add to the big value. So we go from the front, right? Go from the front. And then we can choose, right? We can choose, say, 1 value. How do we choose? No, I think it should be a counter, right? It should be a counter. So 1 have 1 occurrence, 2 occurrence. So I'll have a counter. So I give it a value, right? And then I need to fit to the final. I need another value. And then the question becomes, I'm going to find among, and it could be, yeah, we just, yeah, so the, hold on. So we have a counter, right? And when we go from the big value, and after we get the big value, right, then I'm going to call the same function to, yeah, because I have the big value, so this is like what we want to achieve, right? And we have the original value we need to achieve, and then we use the big value, so we go the original value, the target, minus the big value, that's the remaining value, right? And then we'll look into the same counter and to see if we can get something out from the remaining value. Okay, and then what? How do we find out? We always go from big to small. That is not. Think. Only thing that's just like if it's not deterministic, right? If we have a case that is not deterministic, and what do we do? I can always say, okay, from this, I'm going to pick a small one, and then keep going. Yeah, so I can say I pick myself, right? Num's length is 16. 16. Feels like it got something to do with 16, right? the number itself is huge. Yeah, it just means that there could be a lot of conditions we need to consider. So if we check this, what if we keep checking the big ones, right? We keep checking the big ones. We check the big ones, then we move on, right? We move on, we move on. And if we fail, we backtrack, right? We fail, we backtrack, which means picking this one is not going to work. So we need to pick someone smaller. Someone smaller. Yeah, it means only 16, right? Only 16. So we pick someone smaller. Okay. And then we're going to finish all the picking, right? Pick someone smaller. And then what? Think about the recursion, right? Recursion, what we have is a target. The target value we want to reach, right? And then we give our counter. That's it. That's a recursion. The target value we want to reach and the counter, right? And so if the target value is larger than the largest available value in the counter, then we return false. If the target value is smaller, then we use the largest value. We always try to use the largest value, right? And then we have the remaining. So we call the function again, which is the remaining target with a counter. And that will give us whether it's true or false, right? What if it's true? What if it's like say 3 and then we pick 1, right? And then remaining is 1. We're going to it, and then we pick 1. It's done. So now what? We return true, 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 true. And the first level, so the first level, right? First level. And every time they pick, they're gonna minus, like keep track, right? Copy it. Copy it. We're gonna copy it. So we don't have to, yeah, we're gonna copy the dictionary. Because there's only 16, it's small, so we don't have to keep track of the state. So at each recursion level, we have the state. But are we supposed to go all the way to the end? We're talking about two different recursions. So one is to get a target, right? So yeah, so we have the actual target, and we have the counter. So whatever the counter's current state is, we try to find if there's a way that we can get the value out of it, right? And let's say we run that, But what if there are multiple ways that we can get it? Well, if there are multiple ways, that's the current problem, right? So because given a target, there could be many ways, like involving a value. There could be many ways to form the target. So what we're saying is we have to find all of these ways, right? We find all of them. Okay. Let's just say we find all of them, and after we find all of them, we're going to return a new state, a new dictionary, a new counter, right? A new counter. And the new counter represents the state after we find it. So yeah, we're given the current one, current value, current large. We go large to small, right? So we get a current value, and then we obtain a whole bunch of possibilities. And for each possibility, right, then we keep recursion. For each possibility, we go look for the next one, right? For each possibility, we go look for the next one. And by going to look for the next one, what we're talking about is to look for the next target, right? We look for the next target. Okay, so can we cache? I mean, dictionary cannot be cached. But who gets picked, right? Who gets picked can be cached. And because of the 16, we think we can use like a bitmap, right? Let's say we have a bitmap. And who gets picked is going to be marked, right? So that is a state. And if you think about it, because there's only 16, right? So we don't use a counter. We use a bitmap to represent the state, right? We use a bitmap to represent the state of who has been picked. So given each value, so I pick this, right? And then we pass this as a state down. And then what we're going to return is a bunch of these values, which contains different states that can form the target value, right? And once we've done that, hold on. So again, we're talking about what are we talking about? Talking about secure one value, which is the current largest value, right? And then, so securing from the right side, we go in, right? From the right side going in, we try to find the first value that has not been checked, and then that will be our base. And then we run another algorithm, which is going from this base to look for any possibilities to form, right? If it can, if it cannot. And then that one will give us a bunch of new states, right? And then from each new state, we're going to run the exact same thing, right? We'll run the exact same thing. And then eventually, right, so it'll be like this, right? So we'll have initially everything is 0, right? Everything is 0. And we're going to check the rightmost value, right? So we have a state, and we have the index, right? State, we have index, and of course we have the target, and that target is the true target. So we call this function, and this function will find all the states that can form, that uses the current I, right? All the state that uses the current I, that will, so this one will return, right? This one will return a list, right? List all the states that can form a target value using the current I. But in that case, do we even need to sort? We don't even need to sort, right? We shall, but we don't need to. I mean, we like the easy check. We can just check the largest value, right? We have a total value, we have the largest value, and then we're good. But sorting is so cheap. It's only 16 values, so we shall sort, right? And then we go from the large one to the small. So the large one, right? We take the value. So this will produce, right? Will produce. So we just gonna go each one. Okay, we just get it, and then we keep running. We get it, we keep running, keep running, and eventually, once we achieve what we have, I mean, it can make it easy because we the index, right? We go from the large to small. If every scan is from large to small, so the next scan we must scan even smaller. Okay, so that's good. So given the current state, given the current this, given the current target, we try to find. If we can find it, now we return. What do we return? We return a state, right? We return a state. Right, so this and each one, and then we run it, right? And then this one will return either a state or we return like a minus value. Okay. Shouldn't we return a list? Yeah, we shall return a list. And every time we do this, I will return a list. We'll return a list of all possibilities, right? Return a list of states. And then for me, I'm just going to aggregating these, right? I'm going to aggregating these states, and I return. So eventually, at the first level, what I'm going to get is a bunch of states, right? That will allow the target value to form what we want, right? So that's like the first level. And once it's done, and then what? Then for each state, right? For each state, we need to keep searching, right? Keep searching. So how do we search for each state? So we have the first, right? So given state. Okay. I would like a queue, right? Yeah, we can like make a queue. The starting state is all empty. And we'll pop this out. And then we look for the first viable one, and we run a DFS to get all possible states. And those will be in a queue. So they will be all pushed into the queue. All right. And then once it's done, when I go back, now we pop each one out. Pop each one in the queue, we pop it out. I mean, it doesn't have to be queue, it could be stack, it doesn't really matter. It's just like we find something, we just push it in, push it in. It's just a list. We just go through the list again. Yeah, and then we'll come out, we go through the list again. For each one, we'll run the same algorithm, right? Yeah. Which is like the second value we're trying to see if we can find. And then the third round, just like after the second round, right? And then the third round and the fourth round. So after 4 rounds, what we want to see is if something comes out, if we all have, if we all have a state, right? So after 4 rounds, we'll get the final states, and we'll see whether the final states are how should I call it? Whether the final states are like everybody's filled, right? That's if everybody's filled in the final state, then that means we're good. If any one of them, then we're good. Otherwise, we're bad. I want to try this. Okay, I want to try this. We might run over time today because I think the difference time between now and I think it's 3 hours, right? Yeah, so it's like 10 o'clock. Yeah, it's like 10 o'clock. Oh my god, I made the same mistake again? The heck? Every single time I have this again. Oh my god. $30. Rename no such file. Oh. This has to be 2. Alright, so let's go copy again. So make sure tomorrow I don't have the same problem. Yeah, that's pretty stupid. Alright. I have a general idea, but I feel like this one is not that simple. It's not quite straightforward. Okay, so we have this, and we decide to sort it. So we're going to say num.sort, right? We decide to sort it, and total equals sum nums. Total equals sum nums, and target will equal to total divided by k, right? If target times k, right, is not equal to total, or we say nums minus 1, the largest value, is larger than target, then return false. So a quick check. Now after the quick check is done, now we have a target state. Okay, so the initial state. So we can just say, let's just call it Q, right? Q is going to be a state. Initial state is 0, right? That's the initial state. Oh, and now we all need n. Let's just do n into len nums, right? That's the initial state. And then we know, because we will go k times, right? We go to k times. And k times. What's the signal for failure? Like if I cannot find it, right? If I cannot find it, I just don't report. Yeah, if I cannot find it, I simply do not report. I report like empty, right? No, I should not report empty. Yeah, you just report empty, which means I cannot find any state that can support the current. Yeah, that's fine. So we have a Q, and then it's not going to be, well, Q is empty. But actually it's, yeah, no. We have to go 3 rounds, K rounds, right? So we'll go K rounds. Yeah, let's just say for this in range K, so we'll go K rounds. And then each round, I'm going to call a DFS, right? So each round, I'm going to call DFS. We're passing for state, right, in Q. So for each round, we have a temp. Temp equals this. So each round, the state in Q. For each state coming out, we're going to call DFS state, right? And then, actually, we need to find the first one, the index, right? That's what we want. We want the index to go with. Like that's the target. So we have the state in Q, and then we say for I in range what? So we're going to go from the rightmost searching, right? Rightmost search to the left, and then we want to find which position that has not been occupied. So I going to be from n minus 1, right, to minus 1, minus 1. And then for each, we're going to check if state and 1 left shift n minus 1 minus I, right? So initially, the first one should be left shift 0 times, right? And then we say we shift 1 time. Because we want to look at n minus 2, so we shift 1 time all the way to 0. If I is 0, then we shift n minus 1 times. We shift n minus 1 times. So when one shifts this, and we do state and end this value, if this value equals 0, right? If it equals 0, then we have it. Then we have it. Then we can break, right? And then we can do I, because I is the index. The index. So we know the state, we know the index, and then we know the current target, which is this target initially. So the DFS is going to give us bunch of state, right? It's like a list of state that can satisfy from I, right, plus whatever is smaller will reach the target. So temp.extend, right? We're gonna extend temp. Does extend return a value? I forgot. So let's say A is equal to 1, 2, 3. B is equal to, let's say, 4, 5. A.extend B. I think it's, yeah, change A. So we just call it temp.extend, right? And after temp extend, and then we'll go to the next state, right? So each one is different. So temp extend again. Once we go through all the states, so we get the new states, which has accomplished one, you can say one subset. Right? We get one subset done. Okay, so now we have one subset done. Now we're gonna say Q will equal to temp, right? Come back, and try to get the second subset, and we're also going to find the first one that is 0, that has not been set before. Oh, the state needs to change. So once we do this, the DFS has to be this. What is the state? Well, it depends on whether we want to count the i's position or not when we pass it down. Let me think. So we say it's a state, and this is the value we want to take right now. Yeah, let's do it in DFS. Which means the first thing we do is we will change the state, right? We change the state. That's the first thing we do, and then we do whatever else we need to do. Okay, so Q will equal to temp, and we'll go back up, go to the next K, and then we run exactly the same thing. All right, exactly the same thing. And then, boom, going back up, and then, boom, going back up. And once we're done, right? Once we are done, go through all K, right? Now what do? Now we're gonna go, and we have a Q, right? We're in Q. So I think if we have value in Q, then that means we have found. So we can just say return len Q is larger than 0. If it's larger than 0, then we're good, right? All right, so that's that. Now we're going to define DFS, right? So let's do that, which we can do it here. Def DFS, right? So DFS, we need state, we need index, and we need target. This one is going to return a list of integers, which is a list of states. All right, so I'm passing first thing, state equals state or equal or 1 left shift index. And also put a parentheses. Is that true? Left shift index. So if my index is 0, then left shift 0. If my index is no, it's not. It's n minus 1. Right, it's n minus 1. Don't forget, it's going to be n minus 1 minus index. That's the first thing we do. Right, we left shift that much. Because index is the actual index. So we need the n minus 1, so that's, yeah, so that means we're taking index. Now, once we take the index, next thing we do is we're going to search from index going down, right? We're going to search from index going down. So we're going to say result is this, right? And then we're going to say for, right, for j in range from index -1, right, to -1, -1. Each one, we're going to check the number value, and when this C, we say if what? If target, oh, do we change? Oh, that's a good question. Are we taking it or do we not take it? Yeah, I think we should take it here and also modify the target as well, right? So the target will be modified and the state is modified as well. The state, it represents, we already checked it. The target, yeah, so base, oh, hold on. What would be the best? So this is the starting point. Let's make the index the starting point. The starting point for search. The state is a fresh state and we haven't added anything. Yeah, that would be better. So that just means we're going to do this. State, right, or one, right, state or one, left shift n -1 minus I, right, so that's the new state. Okay, and then this is going to be I -1. So we take I, so we're going to go -1, and that's going to be target minus nums I, right? This is the new state. This is the new starting point, and then this is the remaining target. So here, so we don't have to do this. And the first thing we say, if, right, if, what if the target is already 0? Right? If target is 0, right, if target is 0, then we're going to return state. I mean, that's a good state. We return it. If target is smaller than 0, right, then we return empty, which means we cannot find anything. Otherwise, we have result, and then this is going to be from index to this, right? Then we don't check, right? We don't check. We just simply say we're going to call DFS, right, with the current state or 1 left shift then -1 minus j, right? So that's the new state. We take every single one. Oh, hold on. It has to be a one that has not been taken before. So I have to also say if state and 1 left shift and -1 minus j. If this is equal to 0, then we call DFS. Right? Then we call DFS. Now we're searching for why do we break? Good question. Why do we break? Because we want to start at the biggest value, right? Because if we do the biggest value, we get out everything, and then if we keep going, right? So we have a covenant state. Now find the biggest value, and I will keep going, and then those will be smaller values, right? The smaller values, what they do, they're not taking the biggest value into account, because everybody needs to So yeah, so I just go biggest value and find everything that can fit biggest value. I mean, if the biggest value cannot fit, then there's no point moving on, right? Yes. If the biggest value cannot do, there's no point moving on. That's why we stop the biggest value, find the biggest value that has not been fitted yet, and we fit it, right? We fit it from the biggest value. If biggest value, if it's fit, and then next one, yeah, I think this is a good logic. But I just realized one thing. Temp is here, right? If this gives me nothing, right? If like temp, I take whatever state, I take the current one, and then it just can't find anybody, right? What if I cannot find anybody? Then yeah, then Q will be nothing, and then we'll be gone. We'll be done. That just means one value cannot be fit into any possible combination, right? I think that's reasonable. One value cannot be fit into any combination, which means if I have a Q, right? If I have if temp, if not temp, right? Then we just can return false. Like anytime if we cannot find anything, I'm sure return false. If else, we keep going, keep going, and then once we can get out, right? Because we have the last round, we can get out, then we shall return true. Okay. So now, but for this one, right? For each one is 0, right? And then, if it's 0, that means we have not checked it yet. So what do? We do this, and then we do, so we take j, right? So j is already taken, so the next one should be j minus 1. And then we target minus nums j, right? And then that's going to be res.extend this thing. Of this res.extend, right? And then when this one is done, I come back, the state is still the original state, right? Still original state. So we keep searching, and then boom, 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 get the res. Once we're all done, turn res. All right, I think we're ready to run some test case. So the first one, 4, 3, 2, 3, 5, 2, 1, 4, so true. Second one, 1, 2, 3, 4, 3, that'll be false. Right, this one we pass in nums. That's it. Can partition k sub nums. Try it. Too many values to unpack. Oh, we have also the k, k. Oh, forgot to pass in k. Oh, these pass. Let's try our luck. You want some other values? Edge case, 1. And, oh, k has to be 1. Right? Because 1 smaller equal to k. True and true. I just submit. It's late, so if it's wrong, then we can just check it. Oh, We got accepted. Huh. So how should I call it? I think this is quite a complex problem. So to solve it, so first of all, we can easily eliminate um, the impossible cases, right? Eliminate the impossible cases. There are two types of impossible cases. One, the total sum divided by k is not an integer. Two, the largest value in nums is larger than target. Right. These two we can eliminate immediately. And then we make sure that nums is sorted. Make sure that num is sorted. Then we will start from the largest value going downwards, right? Going downwards. For each large value, we find all possible states that can form our target with such large value, right? Then after that, we go through each of the state and find the next large value and produce all the states that allow the next large value to form, to accumulate to the target. We keep doing this, right, for k times until we encounter two scenarios. One, for the next large value, there is no state that can accumulate to the target with the next large value. When this happens, we can return false immediately. Second, we go through all k rounds, and there are still valid states left. In this case, we return true. Now, the algorithm to find all the states that allows a large value to form the target is a DFS, or is a, what I call it, yeah, is a DFS. We can use backtrack, but that feels cumbersome. Given that the length of the array is only 16, we can use a bitmap, right? Bitmask to serve as the state, right? Serve as state. So each DFS call will return a list of bit masks representing the state, the current state where the large value can sum up with some small values to reach the target. So from the outside, this solution looks like a combination of DFS and BFS. But the BFS is just, the BFS can be replaced by a stack. And it's the BFS is not the critical part. The DFS is. And using bitmask to represent state greatly simplifies the DFS procedure. That is, we don't have to backtrack. Right? We don't have to backtrack. We can keep the original state intact. Runtime, no idea. No idea the runtime. Every time this type of problem is just very complicated. No idea the runtime. So, no idea the time complexity. I mean, this is O and log n here because we sorted it. DFS. Well, worst case scenario, right? You can given each position, we'll take each position and then go everything, and take each position, go everything, and take. So we're doing. What is this? It's probably 2 to the n. Yeah. It feels. But it feels. O 2 to the n to me. Yeah, let's see. Let's see how's our performance. Yeah, not too bad. 62 milliseconds, right? So 62 milliseconds, and we clocked in 59%. All right, let's take a look. And now we're in 3 minutes. Not too bad. Medium question, 1143. I bet people are going to complain. LeetCode 1143. Right? People are going to complain. People always complain. Which is fun, right? From time to time, you see people's complaint. Oh, it's locked. Oh, wait. What? Hold on. That is not today's question. Oh, we missed it. Did we? That's the longest common subsequence. Oh, we entered, oh shoot. 698. Oh, that's LCS? That's a I hope there is something different for every out, because LCS is very simple. It's not, okay, again, it's not simple. LCS is not simple if you haven't done it before. 698, so we need to go for 698. They already released the next one. 698. Yeah, it's also a longest common subset. Why this one will still be? Oh, it's because it's at top. All right, so it's not 698. Release before midnight. It's not midnight yet. It's like what 10 something. Good question. 698. Let's take a bit mask. Okay, top down bit mask. DP on subset. Simple, huh? Simple code. Can cache. Dev mod. Ah, dev mod. Come on, man. Max is larger, and then length. All right, let's see. 2 to the n times n. All right. Matchsticks to square. Divide nums into k, with some L equal, so each subset has a sum that's equal to this. Now we just need to find if there exists a way to divide num into subsets whose sum of each subset equals yes. Let dp mask be the remainder after dividing numbers represented by the mask. The ith bit is 1 representing the appearance of if this dp this equal to 0, the remainder after dividing. If dp this is 0, that means we can divide. Okay. Oh, I think what it does is slightly different logic. Let me see. If mask is 0, return 0. Wait, what does it mean? The remainder after dividing numbers represented by bmask mask, where ith appearance of this. If this is 0, I mean we can divide all nums into subsets successfully. Hold on, I don't understand. The remainder after dividing numbers. I think the remainder. Let's read. If mask is 0, return 0. Okay, so for I in range n, if mask right shift I. Okay, so the starting point is everybody's 1, right? The starting point is everybody's 1. So I say if it's a 1, mask right shift, mask right shift. Yes, mask right shift seems to be a better way, huh? Mask right shift and 1. So we check. Mask right shift and we check. Okay. So if it's 1, then new mask equals this. Okay, we take that value, right? Take that value and remain equal to dp new mask. Okay, dp new mask is the value computed from this. If it's -1, continue, can be divided. Otherwise, we say remain plus, oh, it's the remain. Oh, I know what remain means. Remain, the DP will return the remainder. So how much is left that haven't been counted into the subset sum? So we say if this plus this is smaller or equal to this, right? Why do you do that? You can just return remain plus this because they're smaller or equal to. I don't understand. This is weird. You said if remain plus hold on. Remain equals the new mask. So what does that do? What that do is after we put the DP new mask all together, we will get a remainder value. We'll get a remainder value that's missing, right? Like after we arrange everything, okay? So just after we arrange everything according to the subset sum, what is remain? And then if it's -1, that means we cannot do. Otherwise, this together smaller than this. Oh, because we want 0. I see. If it's smaller, so if the remain plus myself is smaller than the subset sum, then I return this. But still, and this will, I will be returned. Shouldn't be subset sum remain plus nums. And if it's equal, it will return 0. And if it's smaller, it will return remain plus nums. Does that remain? Remain plus the current value. So we take the current value, right? We take the current value. Now what we ask is the rest of you, right? The rest of you, what can you get? So what you can get is whatever value that you can get. Right, you add, or whatever, like I don't care. So given this state, right, given this state, what value can you produce? Well, there's only one value. Because I return immediately. I don't understand. But in my case, I test out all the possibilities, right? I test out all of them. In this case, I just say if remain plus this is smaller or equal to, then I return. And that DP mask is done. So what, like if I go first one, I have a new mask, right? And then new mask coming in, or a second one. And then a third one. If everybody has been taken, it's -1. Or if mask is a 0, then that's a 0. Then remains will be 0, right? And the subset sum doesn't change. Hold on. I into subsets whose sum for each sub equals this. dp mask be the remainder after dividing numbers represented by bin mask. After dividing. Yeah, I understand this is whoever has not been taken yet, and then I take it, and once I take it, I will get a new mask, right? I'll get a new mask, and I run dp on a new mask, and this new mask will go take the first one that's not taken yet, and we'll run a new mask. Yeah, so this one is actually initially going to go just one by one. It'll run through everything until the new mask is 0, everything taken, then I return 0. So it returns 0, and it's a 0. So that thing is returning 0 plus nums I. Zero plus nums I. Okay. That will be total value that this new mask can produce. Well, we're allowed to produce. Right? And then, so basically it's like we take the current value and the remaining value, right? And the remaining value, we want to see how much they can produce. Like how much they can produce that it's also smaller or equal to the subsection. If they can produce, then I will include and I return as well. Right? And at one time, you cannot. I still don't understand. I have a new mask. I'm called DP new mask. I need some other help. Let's see. Other people give me. Backtrack. No, I don't like backtracking. How do you even read this? Visit bin mask. I like bin mask. All right. dp mask, possibility to put numbers with mask into our subsets. Not possible, and we return t if it's possible. T is a remainder when we divide sum of all used numbers so far by basket. How many we need to put in each group. Then to check if we can do it. We check the last number we put and check all possible options. Example, imagine we have this. It means we already take number A0, A1, and A3. It doesn't matter where we start. Then to evaluate dp mask, we look at 0, 1, 0, 1, 0, 0, 1, 0, 0, 1, and 0, 0, 1, 1, and try to add a missing bit. Right, so we have already taken these numbers. Now we and to evaluate dp mask, we need to look at this. Sorted, div mod. Yeah, this is fine. dp is fine. For mask in, so we have all the masks, right? And for each mask, J gonna go every single one, and this means neighbor. Mask this one, left shift J, right? With the next one to go, right? Next one to go. Next one to go. And we say if, yeah, so this one means the next one to go. If this is 1, right, that means we can go, and neighbor is larger equal to 0, which means the neighbor still has something left to give. I think that's what it means. And neighbor plus nums J is smaller or equal to basket. So again, what does dp save? Return -1 if this partition is not possible. And return t logical 0 if it is possible. T is a remainder that we divide sum of all used numbers so far by basket. We divide by basket. What is the remaining? The sum of all used numbers divided by basket. Okay, that's a remainder. So something that's still out there that's not been matched yet. All right. So what we say is a neighbor, which is a remainder, plus the current value is smaller or equal to the basket. That means this is a valid state. I think this is what it means. It's a valid state. So we do dp mask. Sorry. The current mask, right? and we get a neighbor. We get a neighbor. We start with -1, everybody. And we start with 0. And the neighbor is going to be one left. Wait, we start, the masks start. So the first one we find, neighbor plus, neighbor just like the next one we're going to take, right? The next one we're going to take. If that plus nums j is smaller, that means that's a good companion for nums j. And TP mask will be this one. Oh, okay. The neighbor plus nums j is smaller than basket. And it will be this one. I still don't understand. The neighbor, that one is just the value, right? The remainder value. Okay, it's the remainder value. The remainder value plus the current value. If it's smaller or you go to basket, then I just break it. I don't keep searching. So given a state, we have 3 to go. And if one of them matches, then we say we just stop. Why? I mean, we are doing the reverse search, so we go from big value to small value, right? We're going from big value to small value. So we say if neighbor, what is neighbor? Neighbor is, if I take the current value, right? So I give it a mask, and if I take one of the values, if I take it, that's the neighbor, right? Okay, so that neighbor is the remainder of this state, which is just, and that is total sum of this divided by basket, right? The total sum divided by basket. Yes, the total sum divided by basket. Okay, and then check my current value, we add to it. Right, we add to it. What if it's bigger? I think this represents a partition already. Because we are never getting above basket. So think about it. Right, we're never going above basket. So the dp value is just how the remainder of the total sum divided by basket, right? If we think about it, it's already partitioned, so it's one of the partition that's lacking, right? And it represents how much has already been filled, right? How much has already been filled for each state. So for a state, dp of that state is how much has been filled. And then, given a mask, right, so the current state, it's actually the previous state, right? It's previous. This is actually a future state. So like if we take the current value, so we take the current value, right? If we take the current value, we will have a new state, and we need to find out the remainder of this new state, right? The remainder of this new state. And if the remainder of the new state is smaller than the basket, smaller than the value, the target value, when we add a current one, so we can add a current one, so that will be a partition. So this is a partition, right? I will be included, and that's a partition, because all the other partitions are correct. So I add my to it, so I say that is a correct partition with me involved in this state. Because, but why do we break? Well, that's because we're going through every single state. We're going through every single state. And I break because if I don't break, what's going to happen if I don't break? Well, we'll keep going for the next one, right? We'll go for the next one. Now we go for the next one. So we take this, right, we're going for the next one. Those are the values that is remaining. And the next one will give us a new remainder. Now we want to use the new remainder plus the current one. Yeah, why do we break? It didn't make any sense to break. Yeah, we already taken these, I understand, as current value. So we want to take the next one. So we want to evaluate this. We need to look at all these. But what you're saying is if one of them functions, then we don't look at the others. The mask is getting bigger, right? So mask will go from small, which is all 0. That's the first one, or 0. That means everybody's taken. dp0 is 0. How are you taking numbers? So initially, so no number is taken. So the remainder is 0. Right? And none of them will pass, because if you do this exclusive OR, the mask and this will be 0. So initially nobody. And now we go to the first state. Right, so one of them gets taken. So if one of them gets taken, and then we say there's only one, right? So we say front, look, and then we look for, yeah, we got one value, and this, and neighbor is 0, because the previous one is 0. It's nothing, we accumulated nothing. So now will be this plus what we have. And we're going to end it, okay? I'll get another one, which is this one is taken, all right? So we want to calculate this one. And then we go this, okay. This will also, this one is taken, right? Okay. Now I have 2, like 3, like state is 3. So the first one is good. First one is good. And then we're just saying, if we take this, we're asking, can we add that? Right? That's what it is. It's a remainder, right? The neighbor is remainder. So remainder plus this. If it's good, then that is it. What? No, we'll go this one first, right? So it's the bigger value. So we say, we're going to take the bigger value. And then we have the remaining. Right, so the current nums j is the bigger value. Remember, nums j is the bigger value. And we say for the remaining, if remaining is too big, then no good. But if the remaining is small, then I can squeeze in. But why we only evaluate the first one? Right? Now that's the current state. The current state, we have a bunch of values, right? And then we want to know if we take this value, we see the remaining, right? If this value and plus the remainder of the remaining is too big, then we cannot partition. But if this one plus remaining is good, right? It's good, then we say we can partition. What if there will be better options? Like taking this, and then we got this remaining, right? And if it's not good, we can take this, and when we take this, this is the remaining, and we take this, and we have remaining, and when the remaining is good, right? The remaining is good, so this is a good state. So we record what this is, and we don't keep going. Why do we not keep going? Like exactly, why do we not keep going? What if like the current option is not good? If it's smaller equal to basket, alright, I need more explanation. Somebody come, give me some help. I still don't understand. The operation. Alright, let's go most votes. backtracking. Which was reference. And I also consider this. I represent A as a bit mask with length 5. If 4-bit is set, then it means its element is present in a subset. So this represents a subset of T4. Now the benefiting bit, now we can set the ith bit unset check. Okay, these are just basic. Third is present. Each number and a sum in binary define whether the array can be partitioned into k subsets of equal sum. K subsets of equal sum. Two arrays of size. All sum subsets. dpi indicates whether array of length I can partition into k subsets of equal sum. Total scores the sum of subsets with sum less than or equal to target sum. Hold on. We have all the states. We have all the states, right? Then the job is we go through every single state. We compute the sum of these values, right? That's what we do. We compute the sum of all values, and given a sum, given a state, right? If I know, let's say we always know the smaller state's value, so this will be the sum, right? Sum. Now, given a higher state, which will have more values in it. And what we want to know is when we add the target value, when we add it to the target value, what will happen, right? Because this is the remainder. We've been talking about the remainder. It's a remainder. So if the value we have is already bigger, right, which means the sum of these two values is already bigger, then this is not a good partition. So yeah, each one is a partition. Think of each one as a partition, right? So then that's not good, not a good option. Right? It's not a good option. Now it's only a good option for partition because the partition just means some partitions, and then we have some left, right? Some left. So pick one value, and then they have partition, right? They have partition, and then if I add to it, at least a smaller value, that is good, a good state. Now with the same state, I can also take this one and try that. Yeah, the question is why we don't try every single one of them. It seems to me that you have to try every single one of them, right? And with that one, you pick, and you have the remaining, and you run the same check, right? And this has to check with that. But then the problem is which one do you keep, right? Which one do you keep? Because they all represent the same state. Yeah, they represent the same state. Yeah, so it's like either like a 1 plus 2, 3, right? So the state represented by 2, 3, and that 1 plus that. Or it's going to be 2 plus 1, 3. Oh, the result is the same. But why do we keep going? Because they might have different partitions. Yeah, so like we're given some value, right? Given like certain numbers we can pick. But there are different ways to partition it, right? There are different ways to partition it. We can partition it like all 3 together. We can partition it as all 1s, right? But whatever the way we partition, we will have a remainder value. The remainder value is if we partition trying to get to the target and what is left, right? What is left. So if that's the case, I add my current value to it. So it's trying to produce the current mask, right? Current mask. And put my value into it, and it turns out that that will be a good candidate for the next round. And then I just escape. I don't keep checking the rest. Why do I not check the rest? Because that's the only time that my state will appear. Right? If I don't keep checking, the value is determined just by the first time I do the check. Why do we stop? Right? I do the first check, and then say, okay, everything works. Right? Everything works. And that's it. I don't keep moving on. But I can keep moving on, and there will be a different state. But it is the same state, right? We're just trying to add different, trying to pick different values out of it. But it is the same state. Oh, after all, it's going to be the same state. So I think what this implies is if it is possible, right? If it is possible, then there is only one way to partition. It's like if we have 1, 3, 4, or if I have a set that contains 1, 3, 4, and we want to calculate the remainder for 1, 3, 4, which means if we partition 1, 3, 4, what's going to be the remainder? So what we can do is we can say, okay, I'm going to do 1 plus 3, 4. So 3, 4 are going to compute. We're already computing. 3, 4 computed their partition. And then if their partition result to 1 is too big, right? So the partition, let's say, cannot do it with 1 and whatever the remainder they have partitioned. It's not going to work. Okay. So now I say I switch to the next one. Right. So let's say the second one comes out, and the remaining or partition. And then it failed. We keep moving, we keep going, and until at a point, we'll have it works, right? Which it just means this state, the current state, will work. Okay. But if I keep going on, I might have other ways that can make the current state work. And the question is just, why do we stop at the first instance? Right? That's just something I don't understand. Why do we stop? Right? I kind of understand that we are going through every single state, and we're checking whether each state supports, right? Whether each state supports the partitions. And then we use the remainder to indicate whether the current state, how much more the current state, how much more what's the extra of the current state after we do the partition, right? And I can have many partitions. Some will be good, some will be bad, right? Like if I have two values, I can partition by add them together or each individual, right? So that is determined. We have two values, we take one out, and we look at the other one, right? And if the other one is too big, if I plus the other one is too big, then it's impossible for us to form anything. Yes, if I plus the other one is it's a smaller value, right? Smaller value, so we can get a remainder. So what does that mean? Right? What does that mean? What does that mean? It's the sum, right? It's the sum. It's the sum. Yeah, we're talking about the sum of everybody, right? We calculate the sum of everybody. Sum of everybody, which means we can partition the sum of everyone, right? And then we can still doesn't make sense to me. We have the sum, right? If it's an individual, and everyone just gets its individual. Unless you're too big, then you will remain -1, I think. I want to understand this thing. I really, really want to understand this thing. Yeah, this is classic question. All right, I have Geek for geek. Oh, it's hard here. Sum of subsets of all the subsets. I don't think this is the same method. Subset sum. Well, I guess I'll end it today because I need to go to bed. But this is just, I still don't understand. I still can't figure out like what the solution means. Clear explanation. Yeah, I've been here before. Let's try to read again. So each subset has a sum. To define if there exists a way to divide nums into subsets whose sum of each subset equals this. True. If dp mask be a remainder after dividing numbers represented by bmask mask after dividing numbers can divide all nums into subsets successfully. But are you saying the remainder will be different? Okay, hold on. What we're saying is, if this gives us perfect remainder, then we add to it, then we're good, right? So at each step, that's just a sum. That's just a sum. But if the remainder is too big, right? If the remainder is too big, then we don't do it. Right? Is that what we're saying? If the remainder is too big, like what we want, I want to add my value, right? But if I remove my value, the remainder values, they tell me that the way they partition, if they want to partition, the value they get is too big. Then if I add to it, I add to that partition, that weight of partition, and it's not going to work. So I cannot be added to that partition. So I go to the next one, right? I go to the next one. Yeah, so I go to the next one. Can't divide by using new mask. The new mask cannot divide. So go to the next one. And this one can divide. But can divide is the remainder. So this, I say, divide by this, we have a remainder. And we always keep the remainder smaller than the subset sum. How could it be larger then? It could be larger. Num's I could be huge. Like if we have the remain will be small, right? Remain will be small. So remain plus num's I could be like num's I. If num's I is big, the remain plus num's I is going to be big. So we don't do it. Now we go for the next one. Right, I'll go for the next one. And then the next one we'll have a new remain because we change the state. Right, we change the state and we get a new remain. Get the new remain. And then this new remain, I'll try to see if that fit. Everybody got a remain, but just that it's different. Right? They have different remain because we are partitioning differently. Right? We're partitioning differently. So we have different values. We have like 1 to 3 partition, and then we're going to add 4. Or 1 to 4 partition and add 3. Right? And each time partition, we try to make it still viable. So if the first type of partition is successful, that means with these 4 values, we can have a partition that is successful. But why do we not keep going? Yeah, that's the biggest problem I have. Why do we stop? Why do we stop? This is the only chance we're gonna hit this. What if this way of partitioning is not working, while another way of partitioning is working? But on the other hand, the result is the same, right? Like, no matter how we partition, if we're given a certain number of values, right? If we're given a certain number of values, no matter how we partition, if they divide by the subset sum, right? The total sum divided by subset sum shall be 0. But it could be that it's like 117, right? we want to divide by 3. So we have 1. Oh, now we add it, it's going to explode. Alright, I think I'll end it today, and I'll keep thinking. This is yeah, and I want to write it tomorrow too, so I'm going to leave it open and see if I can figure it out tomorrow. Alright, I will see you guys, well, not tomorrow, this is today, in a couple hours. Adios.